quantity in terms of a node voltage. And here, same thing, except that it would be in terms of what? Mesh current. Okay, we'll do the same problem again, just using mesh current analysis after we get done with the one with doing it using node voltage analysis. Okay, so we do have a dependent source here. So we can't ignore that step. Sometimes you don't have a dependent source, so you can ignore that step, but we can't here. So what's the controlling quantity here? IQ. The controlling quantity for this is the quantity that it depends on. So it's the IQ. Can I write IQ in terms of node voltage? Yes, because look at this node voltage here is VA, which is the voltage across that 15 ohm resistor. So, using Ohm's law, IQ is VA over 15. Give you a hint, that's wrong. What's wrong with it? Look at, it's not really following Ohm's law because I have the arrow of the current pointing into the negative end of the voltage. So that means I have to put a negative sign here. Right, because Ohm's law says, okay, let me just pull this out. This is what we have. We have VA, and then we've got IQ like that, which is the same as minus IQ like that. Right? This is equivalent to that. Okay. IQ pointing up is equivalent to minus IQ pointing down. But now, this picture here looks more like our definition of Ohm's law. So we've got V equals IR, so but I is minus IQ, R is 15, and so that's how I got IQ is minus VA over 15. So be careful about that. Okay, so now we've done this step here. I have written the controlling quantity of my dependent source in terms of, in this case, a node voltage. So I'm done with that step. Now I have to identify any supernodes you have, because this is node voltage analysis, and write an equation for it. Okay, so it's not just enough to identify it, you actually have to write an equation. So let's go back to that definition of a supernode. Remember what it was? Any voltage source and the two nodes on either side. Do I have a voltage source? No. So I'm done with that step, because there's no voltage sources. But if there was a voltage source, I'd have to do something. But since I don't, okay, now for node voltage analysis, the last step is to write Kirchhoff's current law for all non-reference nodes. All right, so I don't have to do Kirchhoff's current law here, but I do need to do Kirchhoff's current law at node A, and I'll have to do Kirchhoff's current law at node B. Okay, so what does it look like at node A? Well, and I'm going to take currents leaving the node as positive, so I've got minus IQ, minus 4, what is, minus 1.5 IQ, let me just label this IX for now, plus IX equals 0. So that's one equation. I'm not real happy with it because what you want in these equations, okay, by the way, what node voltage analysis will do is it will give you a set, well, both of them will give you a set of n equations in n unknowns. In this case, I've got 2 nodes, and so I want 2 equations. And I want those equations to just have node voltages in them. So I'm not real happy with this because this has currents in it, it's not node voltages, but I can quickly change this equation to just have node voltages because one, I know what this controlling quantity is in terms of a node voltage, so I'll just stick it in. Let me combine these. We've got minus IQ minus 1.5 IQ, so that's minus 2.5 IQ, but I'm going to substitute minus 5A over 15 for IQ because I just want node voltages. Okay, and then minus 4 plus IX is equal to 0. Can I write IX in terms of a node voltage? Yeah, because actually Vx is VA. Right? Does everybody see that VA is equal to Vx? So Ix is equal to 30 times VA. I mean 30 over VA, right? V equals IR, I equals V over R. Okay, so it's going to be 30 over VA. Wait, is that right? I equals V. No.
Should be VA over R.
Yeah. VA over 30. V over, I equals V over R, not R over V, sorry. Okay, now I'm happy, because that equation is an equation with just a node voltage. And then the Kirchhoff's current law at node B will be 1.5 IQ plus 6 plus what? VB over 20. So, and now all I have to do is change the IQ to the node voltage, so I've got 1.5 VA over 15, whoops, minus VA over 15, plus 6, plus VB over 20, and I've got 2 equations and 2 unknowns, right? You can solve 2 equations and 2 unknowns. I'm not going to finish it because that's math. You know how to do math, right? Someone say yes or no.
Yes.
Thank you. Okay. So those are the steps. Okay, we didn't get to do this step because we didn't have a supernode. Let's go through again and do the same problem, but let's do mesh current analysis. I'll do it in blue this time. So I'm going to take my check marks off. And I'm going to get rid of these node voltages. Go back to the original problem. So there it is, there it is. I don't have to label that. Okay, so I'm still looking for Vy, but now I'm doing the same problem, but I'm going to use mesh current analysis instead of node voltage analysis. Oops, what happened to Vy? Oh, that's Vy. So we're done with the first step, right? It's drawn. I think I got everything's labeled. Yeah, it's good. Now I'm going to label the mesh currents. All right, so how many meshes do we have? We've got 4. Okay, so I'm going to label this IA, IB, IC, and ID. I could have labeled it 1, 2, 3, 4, but oh well, I labeled it A, B, C, D. So those are all my mesh currents. So, done with that step. Easy. The first two steps are pretty easy, right? You just draw it, and then you label. In the case of mesh current analysis, you just label all your mesh currents. Okay. I still have a dependent source, and so this step applies to any dependent source. You have to write the controlling quantity in terms of, in this case, I want to write the controlling quantity in terms of a mesh current. So, let's see, the controlling quantity is IQ. Is IQ a mesh current? No, IQ, the mesh currents are IA, B, C, and D. There's no IQ in the mesh currents. So, but can you see what IQ is in terms of a mesh current? Well, you have to look where IQ is in the circuit. So whatever the controlling quantity is, you have to go to where that controlling quantity is in the circuit. And there it is. Can you tell me what IQ is in terms of IA? Isn't it equal to IA? Yeah, so that's pretty simple and straightforward. Let's say the controlling quantity here were IX, just for the fun of it. What would that controlling quantity be in terms of mesh currents? Benson. Remember, so IX is the branch current. We've got two meshes on either side. So isn't IX just going to be IB minus IC? So you're not seeing it? Okay, so I want everybody to make sure that you really understand the concepts of a mesh current and how it relates to branch currents. So IX is the total current in this branch here. IB is the current that circulates in this mesh. IC is the current that circulates in this mesh. So both of these mesh currents are in this branch. So the branch current IX is equal to IB minus IC. Okay, so, but actually my controlling quantity isn't IX, it's IQ, which was even easier. IQ is just IA because IQ is on the perimeter. It's not, there's no mesh on the other side. Okay, so, but sometimes you will have a controlling quantity that is a branch current, which is a combination of the two mesh currents, and so I want to make sure you're able to identify what that controlling quantity is in terms of mesh currents. Okay, how confident are you that you can do that? 100% confident, 0% confident, or somewhere in the middle? Let me see, I want to see a thumb for everybody. Nobody's like totally up?
What was the question?
100% confident you can find the controlling quantity in terms of the mesh current versus 0% confidence, and where are you in between? Okay, well, okay, that's good. Somebody's got a little bit up. Good, okay. All right, so learn, but be sure you don't go to bed tonight until you're really confident of it, and if you're not, then post a question or stay after class or something. I have a few minutes after class, but it's really important. Okay, so now that I've done this step for my problem using mesh current analysis, I've taken I only have one dependent source, so I only have to deal with one controlling quantity, and I've written it in terms of the mesh current. So I'm now on to this one, okay? And in this one, it does apply because we do have some super meshes. So we want to identify them, and that's what you have to do in this step. You have to identify the super meshes and write an equation. Okay, and I'll tell you what the equation is. Okay, first let's identify it. Well, remember a super mesh is just any current source with the mesh on either side. So here's a current source. So here's a super mesh right here. And then here's another current source, and so here's another super mesh. Now this one doesn't really have a mesh on the other side, so you don't have to worry about that one. Okay, so we've identified two super meshes. There are two super meshes in this problem. And what you need to do once you identify a super mesh is you need to write the branch current in terms of the mesh currents on either side. And the branch current, of course, is the actual current of the source. So for this one, the equation is going to look like this. It's going to be, I'm not going to put units on it. 4 is equal to IA minus IB. So there's the equation that I wrote for the first super mesh. And then the equation I'm going to write for the second super mesh is going to be its current, which is 6 in the branch current, in terms of the mesh currents on either side. Is it ID minus IC or IC minus ID? Well, IC is the one going in the same direction as the 6, so it's going to be IC minus ID. Okay, so those are, this step here, this fourth step, gives you the first of your n equations in n unknowns. So I have two equations here that I just got. I'll label them 1 and 2. And I have 4 unknown meshes, mesh currents, so I need 2 more equations. I need 2 more equations. Where am I going to get them? I'm going to get them in this last step, where I'm going to do Kirchhoff's current law. If it's the dual, am I going to use the current law? No, I'm going to use the voltage law. I'm going to do Kirchhoff's voltage law for all non-perimeter See, I'm trying to make it sound the same, but I just can't. It's for all meshes that don't have a current source on the perimeter. So for all meshes that don't have current sources on the perimeter. So that's really just this one here. So let's do Kirchhoff's voltage law for that one. And that will be our third equation. Oops, not sure about my color coding here. And so let's start here. Looks like we've got 15 IA, because that's the voltage drop as you go across that resistor, plus 30. What's this branch current here? It's IB minus IC. And then I'm back. Okay, so there's my third equation. And then the fourth equation is going to come from recognizing that the current source on the perimeter is going to be equal to the mesh current there. So IC, actually it's the negative, right, because they're going in a different direction. It's minus 1.5 IQ, but IQ is IA. And the reason I want it in terms of IA and not IQ is because I want these equations to be all, the unknowns of those equations should just be the mesh currents. Because that's ultimately what you're doing, is when you're using node voltage analysis, you are looking for n equations in n unknowns, where the unknowns are the node voltages. When you're doing mesh current analysis, you're looking for n equations in n unknowns, but the unknowns have to be mesh currents. And in this case, since I've got 4 mesh currents, I'm looking for 4 equations. I got them. I'm done. I am so done with this problem because I don't wanna do the math. I can do I can solve 4 equations and 4 unknowns, but I'm done with this, that's just math, right? I'm done with the circuits part of the problem. Well, or am I? I can certainly find IA, IB, IC, and ID from these equations. Does that give me VY? Yeah, because look at the picture. VY is just going to be 6ID. So once I have ID, then I'm done. All right. That's it. Really be diligent in learning both of these methods this week.